All right. Good morning. Just going back to what we have been looking at with the varieties of equations we have dealt with, and the other day we looked into radical equations and momentarily went into absolute value equations. And looking at resuming with what we have on page 70, and we have among the exercises, can we have once again absolute value equations. And for problem number 90, okay, we're solving for the variable t. And here we have 4 times the absolute value of 2t plus 7, followed by the addition of 2 is equal to 22. And again, we have with this equation, okay, we have multiple steps. And again, you will not distribute 4 over 2t plus 7, for you do not treat the absolute symbolism as you would grouping symbols in the form of parentheses or brackets. Okay, so these are these lines, okay, or bars. They're not your typical operational symbols as they would be with brackets or parentheses, or in some cases braces. And so we'll be looking at isolating the absolute value of 2t plus 7. And first of all, okay, we can move the 2 over upon undoing addition. Okay, so if I take 2 away from both sides, so I'm going to have this equation to become 4 times the absolute value of 2t plus 7 is equal to 22 minus 2, which will be 20. And looking at undoing the presence of 4 on the left-hand side, and we have with division. I'm going to have the absolute value of 2t plus 7 by itself. And so for what we have here, we have the absolute value of 2t plus 7 is equal to 20 over 4, which reduces to 5. And okay, so I have the format where I have the absolute value expression where we have the absolute value of x is set to the absolute value of 2t plus 7. And we have is equal to k, where k is equal to 5, and 5 is a non-negative value. So there will be solutions in the case of t. And as I remove the absolute value bars, okay, so I have going from the absolute value of 2t plus 7 to 2t plus 7. And this expression will be equal to those values that will have an absolute value of 5. That is, those values that will be 5 units away from 0. So you have 5 as well as negative 5. And looking at solving for t's, so I will have a couple of simultaneous equations set up. So we have at the lower end, okay, we have 2t plus 7 is equal to negative 5. Or we could have it that 2t plus 7 is equal to 5. So with 2t plus 7 equal to negative 5. So if I isolate 2t in this equation, so deducting 7, we have 2t is equal to negative 5 minus 7, so this will become negative 12. And we have with division by 2, okay, we're going to have that t is equal to negative 6. And we have with 2t plus 7 equal to 5. Again, taking 7 away from both sides. So we're going to have that 2t is equal to 5 minus 7, which is negative 2. And again, with division by 2, we have that t is equal to negative 1. So we have for our 2 solutions, we have minus 6 and minus 1. Now for what we have in the case of the next problem, okay, we have in number 91, we're looking at solving for the variable c. And we have that negative 3 is equal to the negative of the absolute value of c minus 1, followed by the addition of 1. Okay, so we have the absolute value expression on the right hand side of the equation. So I'm going to isolate the absolute value of c minus 1, and kind of like what we did with the absolute value of 2t plus 7, I'm going to undo the addition that is involved with the term that is on the same side as the absolute value term. Okay, so upon taking 1 away from both sides, okay, so I will have that negative 4 is equal to the negative of the absolute value of c minus 1. And if I undo the negative of the absolute value, so think of it like negative 1 outside, so I can either multiply or divide by negative 1. Okay, so this will become 4 is equal to the absolute value of c minus 1, and it can leave the equation position with the terms as they are, okay, or it can switch the order like a is equal to b, b is equal to a, and just have the absolute value of c minus 1 on the left and 4 on the right. Okay. And taking out the absolute value bars, so we have that c minus 1 is equal to those numbers that will both be 4 units away from 0. So we have both 4 and negative 4. So in setting up the simultaneous equations for c minus 1 equal to negative 4 as well as positive 4, and for both equations, if I add 1 to both sides, so for c minus 1 equal to negative 4, c is going to be equal to negative 4 plus 1, which would be negative 3. And for c minus 1 equal to 4, okay, we're going to have that c is equal to 5. And just like t earlier, c has a couple of distinct values in the possible solutions with minus 3 and 5. Okay. And now for the next item, okay, and we have for number 93, and we have for this equation, okay, so we're looking at solving for the variable y, and for what we have in the case of number 93, we had that 2 is equal to 8 plus the absolute value of 11y plus 4. Okay, so you have another absolute value term on the right hand side of the equation, and if I get the absolute value of 11y plus 4 by itself, I can move this 8 at the front over, and upon subtracting, so we have negative 6 is equal to the absolute value of 11y plus 4. And I could proceed from here, but I'm just going to rewrite this kind of like what I did with the absolute value term consisting of the variable c. I'm just going to move that absolute value expression to the left and have negative 6 to the right. And if you notice, we have the absolute value of x represented by the absolute value of 11y plus 4, and we have for k that is negative 6. However, k is supposed to be a non-negative value, and so because of the negative sign, it turns out that for number 93 there will be no solution for y. Again, absolute value of an expression cannot reduce to a negative constant. Now, in the case of number 94, okay, so this time we're looking at the variable z. So we have that 6 is equal to 7 plus the absolute value of 9z minus 3. And forget the absolute value of 9z minus 3 by itself. So like 93, I'm going to move the coefficient right in front by subtracting. So I have 6 minus 7, okay, becomes negative 1. And we have is equal to the absolute value of 9z minus 3. Again, you can go ahead and state that there is no solution. I'm just going to reorder this. I'm just going to have the absolute value term on the left and that which represents k on the right. And once again, we have with k assigned at negative 1, and k is not supposed to be negative. And just like what was the fate for y in number 93, we have no solution for z in number 94. Okay, now in the case of what we have for the remaining item, okay, 96, a little bit of a trick one. And for this problem, we have not just one absolute value term, but two. And here we have the absolute value of 2a minus 3 is equal to the absolute value of a plus 2. Okay. And in terms of working out for what we have here, there'll be two expressions in a that will have an absolute value of 2a minus 3. And this would be the positive and negative of 2a minus 3. And for those values of a that will have an such that we have an absolute value of a plus 2, and guess what? We're going to have both positive and negative a plus 2. I'm just going to copy this. And in terms of how to go about solving, what I can do is that I can just keep one side here exclusively positive while matching up the positive of the expression on one side and link it with the positive in one capacity of what I have on the other side, as well as the negative of what is on the other side. So I'm going to map the positive of 2a minus 3 and also link it with the negative. And what I mean by this, okay, so I have the positive 2a minus 3 is equal to the positive of a plus 2 and so we have the positive 2a minus 3 is equal to the negative of the quantity of a plus 2. And I'll just mention if I took it the other way, like the negative of 2a minus 3 is equal to the positive of a plus 2 and the negative of 2a minus 3 is equal to the negative of a plus 2. Okay, this part would just lead up to repetition of solutions already attained. Okay, had I chosen these two combinations, the other two would just be repetition. So I'm going to have two solutions still for A. So we have, for this one case, if I work with these two equations, I'm going to have both solutions that I need, okay, to make this set complete. So we have for 2a minus 3, going to have is equal to a plus 2. And looking at solving for a, so I have like terms on both sides of the equation. Okay, so I'm just going to take out the smaller term in a. So I have that a minus 3 is equal to 2. And if a minus 3 is equal to 2, and I have upon adding 3, so we're going to have one solution for a is going to be at 5. And we have with the other setup, okay, so I have removing the parentheses, so I have 2a minus 3 is equal to, and distributing the negative over the quantity of a plus 2, so we have negative a minus 2 and so if I combine variable terms together, so this time I'm going to add a to both sides. So we have that 3a minus 3 is equal to negative 2. And once again we have adding 3 to both sides. Okay, so we have 3a is equal to 1. And we're going to have the a is equal to 1/3. Okay, and I can sort of check for consistency. And now for a at 5, okay, you have 2 times 5 is 10. 10 minus 3 is 7. Absolute value of 7 is 7. And then to the right, you have 5 plus 2 is 7. Absolute value is equal to 7. And we have that 7 is equal to 7. Okay, now with 1/3, okay, say if I have like 2 times 1/3, 2 times 1/3 is 2/3, and 2/3 minus 3. Think of it like 2/3 minus 9/3 is negative 7/3, and the absolute value of negative 7/3 is a positive 7/3. And 1/3 plus 2, think of it like 1/3 plus 6/3 is 7/3. Absolute value of 7/3 is 7/3. So in this capacity, I have this reduces to 7 is equal to 7. And for this term, I have 7/3 is equal to 7/3. And those would be your only two solutions. And had I worked these equations out also, I would have the same respective values throughout. That one a little bit tricky. Yeah, it's enough with one absolute value term, but when you got a couple locked in, it does add a bit of a new dimension. Okay, and now just sort of going back to working with radicals, and tell you what, if we just sort of introduction and perhaps a bit of a partial reintroduction. And we have in the case of equations with non-integer exponents. Okay, and we have just some fundamental rule, and we have, in the case say if you have a fractional exponent, and we'll consider the base to be the letter a, and you have a to the m over n degree. And if I put this in radical terms, we have the nth root of a to the m. And just some cases here. If I have, let's say, x to the 3 halves. Okay, so a is represented by x, m by 3, n by 2. And if I were to write out literally, okay, have the nth root is going to be the second root of a to the m. Again, a is at x, m is going to be at 3. And again, we have a square root. Again, with square roots, you do not typically see the index number. And if I have, let's say we have y to the 4/3. Okay, so n is at 3, m is at 4, a is represented by y. Okay, so in radical notation, so this is going to be the cubic root of y to the 4th. And let's say if I have something like z to the 5/7. Okay, so this is translated out to the 7th root of z to the 5th. Okay, now for equations that have non-integer exponents, okay, these are going to sort of tie in many cases, like the square root property of equality, and we'll also be looking into like the square root property of equality. And let's say that for equations that have non-integer exponents, and we'll say that we have among our examples, say if we're looking at solving for x, and we'll say we have in the first instance, we'll say we have x to the 1/2 is equal to 8. So we're looking at x to the 1/2 is equal to 8. So if I translate what I have from x to the 1/2 to its radical equivalent, so again, you just have like second root of x to the 1st is equal to 8. Again, which is just going to be the square root of x is equal to 8. Okay, now in this particular case, I have the square root of x is equal to 8. And here we have the square roots, or in this case the even root of the expression x is equal to a non-negative constant. So there's going to be a solution here. So I have the square root of x squared is equal to 8 squared. Square root of x squared is x, and 8 squared comes out to 64. So this is going to be your solution. And if you were to check, let's say by calculator, what would happen here is that if you're depending upon how the graphics are displayed, if you have like 64 and you have like the caret symbol, and this is in many other TI models, and you want to enter the fraction 1/2, do not forget to include parentheses. Because if you don't, it'll be like 64 to the 1st divided by 2, which will give you 32 if you don't use parentheses. But for 64, you want all of this to the 1/2 degree, and that will come out to 8. Okay. Now, and let's say that if we have, just sort of changing things up a little, okay, if we have, let's say, 2x plus 2 and we have raised to the 1/3 degree is equal to 4. Alright, so for the 1/3 degree to which we have applied as the power for 2x plus 2, if I rewrite what I have here, so we have the cubic root of 2x plus 2 is equal to 4. And just like what we did when we were working with purely radical equations, again, I can undo the radical by taking the term and raising to the matching exponent. Okay, so in this instance, okay, we're looking at cubing both sides. All right, so we're going to have 2x plus 2, and 4 cubed becomes 64. And we have with our two-step linear equation. Okay, so you have 2x, and 64 minus 2 becomes 62. And we have a division by 2. Okay, so we have for the lone solution for x, okay, we will have at 31. All right, and now another case here. If we have, let's say, x minus 5 to the 1/2, okay, is equal to negative 7. And I translate what I have here from base to a non-integer power to a radical. So you have the square root of x minus 5 is equal to negative 7. And right away, again, just going back to the principal square root rule, again, if you have an even root radical expression, it cannot reduce to a constant that is negative. So right away, this third case has no solution. And say for what we have in the case of a little bit of an added dynamic, and I will kind of mention that the notations will start to get a little bit crowded. Okay, and let's say that if we have the quantity, okay, let's say we have x minus 2 to the 3/2 is equal to 27. So you have that, the quantity of x minus 2 to the 3/2 is equal to 27. Now, if I rewrite what I have here as a radical, okay, so your a is represented by the binomial x minus 2, and again, you have m over n represented by 3/2. Okay, so your nth root, again, you have the square root of x minus 2 to the 3rd is equal to 27. And if I look at taking both sides, okay, so I'm going to undo the radical. Again, it's getting a little bit crowded because you had the square root of an expression that has an exponent. And what I mean by a little bit of a crowding effect is I'm looking at applying another exponent with the 2. And that's because I'm getting rid of the square root. So eliminating the square root, okay, I will have freed up x minus 2 raised to the 3rd. And for the square of 27, so you have 27 times 27, so that would be 729. And looking at what we have for the real valued solutions, for solution in x, so I have x minus 2 to the 3rd equal to 729. Now, I took an exponent to get rid of a radical. And guess what? I'm going to do it the other way around. This time I'm going to take the cube and undo this to get x minus 2 exclusively on the left hand side. So we have the cubic root of x minus 2 raised to the 3rd equal to the cubic root of 729. Okay, so we're going to have on the left, okay, we have x minus 2, and just like some of the other numbers like 1 and 64, 729 is a special kind of number in the sense that not only is it a perfect square number, but it's also a perfect cube. Okay, so 729, you have 27 times 27. And guess what? The number times itself, that would give you 729. That number is going to be at 9. And so we have with x minus 2 equal to 9. Okay, we can come out to x is equal to 11. And before I go any further, so again, the type of radical was a square root, and that was set equal to a non-negative value. So there was going to be a solution for x. In this case, this came out to 11. And let me also mention, not only can the principal square root rule be a focal point, but also we might have the square root property of equality. And in this one, okay, say we have the quantity of x plus 5 to the 2/3, okay, is equal to 4. Okay, and so taking what we have and rewriting, so we have for x plus 5 to the 2/3, okay, equal to 4. So if I translate what I have here going from exponential to radical terms, okay, so we have the cubic root of the quantity of x plus 5 raised to the second is equal to 4. And again, I'm going to undo the presence of the radical upon cubing out both sides. Yeah, from a visual standpoint, okay, there is a bit of concentration that is going to be required. Okay, so you're taking to the third power to undo the presence of the cubic root, and doing this, we still have an exponent whereupon we have the square of x plus 5 is equal to 4 to the third, and 4 to the third is going to be at 64. Okay, and for what we have at this juncture, okay, so you have the square of x plus 5 is equal to 64. Notice I undid the presence of an odd exponent by taking the matching radical and applying it. Okay, but now for the square of x plus 5 equal to 64, okay, this kind of goes back to the seemingly ancient playbook of the square root property of equality. So you have like an expression squared equal to a non-negative constant. And again, going back from the square of x to just x, again you have plus or minus, okay, the square root of p. So just taking what we have here and tailoring in accordance with the square root property of equality. So if we go from the square of x plus 5 to just the first order of x plus 5, so this would be plus or minus the square root of 64 and in this case I have x plus 5 equal to plus or minus 8. And just setting up our simultaneous equations where we have at the lower end x plus 5 is equal to negative 8, and at the upper we have the x plus 5 is equal to 8. Okay, so if I isolate the x's by taking 5 away from both sides, so for x plus 5 equal to negative 8, okay, we have x equal to negative 8 minus 5, which would be negative 13. For x plus 5 equal to 8, okay, so we have that x is equal to 3. And so in this case, we have for x, okay, there will be two solutions with negative 13 and positive 3. And in the case of what we have regarding equations with non-integer exponents, just for the next few moments. Let's see what we get for a couple of items here, and we'll say we have we'll say we have 2 times the quantity of x plus 5 to the 2/3, is equal to 18. And we'll say we have in the second case, we have the quantity of 2x minus 2 to the 3/2 minus 3 is equal to 5. So there's going to be a little bit of an added dimension that it will be to isolate x plus 5 to the 2/3. So you have division involved. And here we have isolation by adding to sort of initiate the process. Okay, if you're still working on these items, that's okay. And for these 2 cases, we are solving for x. Okay, so first of all, we have 2 times the quantity of x plus 5 to the 2/3 is equal to 18. Again, we can isolate our expression in x. Okay, so if we divide both sides by 2, we'll have established that x plus 5 to the 2/3 is equal to 9. Now at the stage, if we translate from exponent to radical, so again, the denominator defines or dictates the type of radical we are going to have. So you have the cubic root, what is going to be the square of the quantity of x plus 5, is equal to 9. And just taking what we have now, so after the rewrite, I'm going to cube both sides. So it has to take care of the radical and have isolated on the left, the square of x plus 5. And upon doing so, so we have what's going to be the square of x plus 5. And again, we have 9 to the 3rd, so you have that number to reappear. So you have 9 times 9 times 9, so this would be 729. And we have with the square root property of equality. Again, so if I go from the square of x plus 5 to just x plus 5, again, I'm going to be taking the positive and negative square root of the constants on the other side. Okay, so we have with 729, it's both a perfect cube and a perfect square. So here we have x plus 5 is going to be equal to plus or minus 27. And just taking what we have now, establishing the simultaneous equations. So we have x plus 5 is equal to negative 27, as well as x plus 5 equal to 27. And we have, upon isolating x in both equations, by taking away 5 throughout, so we have for x plus 5 equal to negative 27. X is going to be negative 27 minus 5, which will be negative 32. For for x plus 5 equal to 27. Okay, so we're going to have the x is equal to 22. And we have, for the results, we have x equal to negative 32 at the lower end and 22 on the upper. All right, and for what we have in the other case, all right, so we have the quantity 2x minus 2 raised to the 3 halves followed by the subtraction of 3 is equal to 5. And if I isolate the quantified expression, so adding 3 to both sides, so I have the quantity of 2x minus 2 to the 3 halves is equal to 8. And if I rewrite going from exponential to radical, so again I'm going to have the square root of what is going to be the cube of 2x minus 2 again I have is equal to 8. And just taking care of the square root, again we're going to have with squaring both sides. Okay, so we have the cube of the quantity of 2x minus 2 which will be freed up after squaring, and then for 8 squared. Okay, so that is going to be 64. And again, just with, if you have odd exponents and I'm eliminating them, you're just going to take the radical, and you're not treating this as you would the square root property of equality. Okay, so just taking the matching root as it is. So again, we're shifting gears. Once again, so going from using exponents to eliminating radicals, now it's the other way around. Okay, so for the cubic root, the cube of 2x minus 2, this will be 2x minus 2. And we have the cubic root of 64 comes out to 4. And isolating 2x, okay, so adding 2 to both sides, okay, so we have 2x is equal to 6. And we have with division by 2, okay, we have our solution to come out to 3. All right. Now, in the case of the set of problems from page 70, okay, and in the continuation, okay, I had mentioned to look into 3 items, okay, from the set. And this is with numbers 115 through 117, and those also involve, okay, non-integer exponents in the equations. Okay, so we have again, so for 115, okay, we have the quantity of 3x plus 1 raised to the 3 halves plus 2, okay, is equal to 66. Again, so I'm looking at solving for x, and if I isolate, again, the variable expression upon taking 2 away from both sides, okay, so we have the quantity 3x plus 1 raised to the 3 halves is equal to 64. And rewriting as a radical, again, so you're looking at the square root The cube of the quantity of 3x plus 1 is equal to 64. And we have with squaring both sides. Yeah, so the right-hand side is going to be a rather large number. Okay, so for what we have here, undoing the square root, squaring both sides. Yeah, and there is a crowding effect, I know, on the left-hand side, but once you square both sides, okay, you're going to have 3x plus 1 raised to the third freed up. Now for the square of 64, okay, this is going to be a large number here. So we have 64 times 64, so this will be 4,096. And now just shifting gears once again to undo the exponent. And undoing the cube. Okay, so the left-hand side, okay, this will become only 3x plus 1. And for 4,096, like that 729 number, this is both a perfect square and a perfect cube. 4,096 is going to be the square of 64, and it is also going to be the cube of 16. And so for what we have in the layout, so for 3x plus 1 is equal to 16. If I isolate, okay, the variable term, okay, we're going to have that 3x is equal to 15. And with division by 3, we have the lone solution for x, which will be 5. And now, in the case of 116, okay, this time we have, once again, solving for x. And this time we have the quantity of 2x minus 1. And this is also going to be raised to the 3 halves. And we have minus 3 is equal to 122. And if we isolate, okay, the variable expression, okay, so we have the quantity of 2x minus 1 to the 3 halves. Okay, we have equal to 122 plus 3, so this will be 125. And a little bit of history repeating, so just going from exponent, non-integer exponent, to its radical equivalent. So you have the square root of the cube of 2x minus 1 again, if we square both sides, so we're going to have here, okay, so I have the cube of 2x minus 1 still. And for the square of 125, okay, so we have a very large number in this case with 15,625. And like the 4096, okay, we also have this to exist as a perfect cube. Yeah, so in comparison to number 115, okay, you had different numbers, but you got the exact same cycle. We have the cubic root on both sides. Okay, so this will come down to 2x minus 1 is equal to, and the cubic root of 15,625, this will be only 25. and we have an isolating the variable term. Okay, so we have that 2x is equal to 26, and with division by 2. Okay, so we have the x is equal to 13. Okay, now for 117, okay, this one, not quite so much work involved, but there is a little mini lesson in its own right that we have in terms of radical reduction. And for 117, now we have that m raised to the 3/4 is equal to 5. And for this one case, if I translate from m to the 3/4 to its radical equivalent, so this is going to be the 4th root of m to the 3rd is equal to 5. And just as I had squared both sides to get rid of square roots and cubed both sides to get rid of cubic roots, I now have the 4th root to take care of, and this will be taken care of by taking both sides and raising to the 4th degree. So as the radical is eliminated, so we'll have m to the 3rd, and for 5 to the 4th, okay, so 5 to the 4th goes to 625. So I have m cubed is equal to 625, and I'm looking at solving for m. So I'm going to take care of the exponent by taking the cubic root of both sides. So the cubic root of m, this goes to m. Now right now we have the cubic root of 625. And I know like Alex likes to go for the radical reduction. So let me just mention some items here. Now for your perfect cubes, okay, in the natural numbers, in case you have like 1 cubed is 1, 2 cubed or 2 times 2 times 2 is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and you have 6 cubed, this would be 216, and 7 cubed, okay, this is 343, and we have 8 cubed or 8 times 8 times 8, that is 512, again 9 cubed is 729, and 10 to the 3rd, that is going to be 1000. Okay. Now regarding the cubic root of 625, okay, now out of the perfect cubes that will go into 625 completely, that is going to be 125. And so we have, upon, say, splitting up the perfect cubic factor, say the cubic root of 125 times the cubic root of 5, as we partition separately, and the cubic root of 125, this will go to 5, and then we have times the cubic root of 5. And so for this reduction, okay, we will have for m, and still in exact terms, we have 5 times the cubic root of 5. Okay, all right. And now, okay, so far we've dealt with, in the solutions, we have had exclusively real values, okay, some rational numbers, some irrational numbers like what we have here, and some as fractions that cannot reduce to whole numbers or integers. Now we have in the next phase kind of a continuation, but just an added realm to look into, along with the real numbers. Okay, we have for this next portion, okay, we have what will be referred to as complex numbers, or what are often referred to as imaginary numbers, but I like to stick with complex numbers. And for complex numbers, okay, now the centerpiece of complex numbers, some books might have it as the letter J, but most will have it as the letter I. And the letter I is going to be in reference to the square root of -1. Now, the square root of a negative is not in the real number system, but in the complex number system. And centerpiece of this is where you're going to have that I squared is equal to -1. Okay. And let's say that for I is equal to the square root of -1. And just to kind of kick things off, okay, say if you're looking at reducing in terms of the letter I, and we'll say we have the square root of -25. And if you dealt with complex numbers before, chances are you already see the result. And I'm just going to sort of partition this out. So this would be like the square root of 25 times the square root of -1. Square root of 25 is 5. And again, square root of -1 refers to I. So you had the square root of -25, okay, reduces to 5i. And let's say we have something like the square root of -18. Okay, now for the square root of -18, okay, what we're going to have here, see if I partition out the -1. Okay, so I have the square root of 18 times the square root of -1. Now we got the square root of, you can write this as the square root of 18i. Okay, but now 18, unlike 25, is not a perfect square number. However, it can be reduced. Okay, so we have with the square root of 18, the highest perfect square that will go into it is going to be 9. So you have the square root of 3 times, back up, square root of 9 times the square root of 2 times I. Now the square root of 9 is going to be 3. And 3 times the square root of 2 times I. And this will be the notation you'll see in your book, but to kind of ensure that the I is not trapped inside the radical, we can say we have 3i times the square root of 2. And another case too where radical reduction will be involved. Okay, so you have the square root of 500. And so by then you can go ahead and write the square root of 500 times I. Just kind of showing a bit of a granular breakdown. So you have with the square root of 500. Okay, so like the highest perfect square that will go into 500, that's going to be 100. And we'll go ahead and split up the factors here. So you have square root of 100 times 5 would be square root of 500. And if I partition separately, square root of 100 times the square root of 5, and we have times I. And it's in the reduction, so this will be 10 times the square root of 5 times I. If we you shuffle the order, just have the I in front of the radical. You could also write this as 10I times the square root of 5. Okay, and in terms of formatting, okay, we're going to have, just for the layout, the standard form of a complex number is going to be a plus bi. Okay, so again, just little reminders. Okay, so we have, again, so we have I is equal to the square root of -1. And if you're in a situation where you have I raised to a multiple power, like if you have I squared, so this will go to -1. And just kind of give you a little bit of backdrop here. If you're looking at reducing in terms of a plus bi, the standard form, so we have as the first case okay. So you have 3 plus the square root of -36 quantified, and you have plus the quantity of 2 plus the square root of -100. Okay, so we have here, okay, I have the square root of -36 and the square root of -100. And say if I just put this in terms of the variable I, so again, the square root of 36 is going to be 6. Now the square root of -36, okay, this will be 6i. And for 2 plus the square root of -100, okay, so this will be 2 plus 10i. And looking at removing the parentheses, so you have 3 plus 6i. Again, you have plus 2 plus 10i. Okay, and just taking what we have here. So you got combining just the numerical constants 3 and 2, so this will come out to 5. And for the complex terms we have in the variable I, have 6i plus 10i, so this will become 16i. And let's say that if we have a situation where we have the square of 3 minus 2i, okay, what this would mean here for the square of 3 minus 2i. So again, just we're in the complex number system, but in terms of taking an expression in parentheses and raising to the second power, if we put in terms of multiplication, this will mean that 3 minus 2i is going to repeat. So you have 3 minus 2i times itself. And if we take what we have here, it's going to let me I'll do it this way. Okay, so you have the quantity 3 minus 2i squared. So you have 3 minus 2i times itself. Now if I take the FOIL, so you have the first product, you have 3 times 3 is 9. Outside product, we have 3 times -2i, so we have a -6i. Inside product, you have negative 2i times 3, so we have another negative 6i. Now we have negative 2i times negative 2i, so this would be a plus 4i squared. Okay, and I want to put this in terms of a constant plus bi. So we're going to have 9, negative 6i minus 6i, that's a negative 12i. Now for 4i squared, okay, recall, okay, so I squared is equal to negative 1. So we have at this phase, have 9 minus 12i plus 4 times I squared, which will be negative 1. So plus 4i squared translates to a negative 4. And if I combine the 9 and the negative 4, so this will be 5. And we have minus 12i. Okay, and say we have in a third case here. Okay, and we'll say that we have so I'm trying to remember how Alex wanted it displayed, because I know that Alex can give one notation and the textbook can give another notation. But let's say if you have a difference of squares that will abound. So you have the quantity of 7 minus 3i times that of 7 plus 3i. So again, if I FOIL out, okay, so you have with the FOIL, say 7 times 7 is 49. Outside product, okay, so you have 7 times 3i, so this would be a plus 21i. Negative 3i times 7, so that's a negative 21i. And negative 3i times positive 3i, so this would be a negative 9i squared. Again, I squared is equal to negative 1. And if you notice, okay, we've got 49. Now we've got a plus 21i, negative 21i. And now technically those terms will cancel out. You have 49 minus 9 times negative 1. And negative 9 times negative 1, this will be a positive 9. Okay, and so this will come out to 58. But I just wanted to mention, I'm trying to remember if Alex just takes just the single term after the other part of the set is canceled out. But another way you could write this, okay, is that you have your A term and the A plus BI to be at 58. And if I had to write this in any other way to include the I term, well, when terms cancel, the result is 0, and when they are in the letter I, you could write this as 58 plus 0i. Again, 0i still amounts to 0, but if I had to give the formal notation to include the I term, it would have to be 0i. And again, just for tonight, again, the Alex homework section R5, solving quadratic and rational equations, again, due tonight. And then Wednesday night, you had the Alex homework section R5. Again, that'll be the part with solving radical and absolute value equations. Again, just for the class activity 1 set, which is accessible through Alex, that will be due Saturday night at 11:59 p.m. And again, just items to go ahead and be looking into, and future topics in the mix will be working with complex conjugates, as well as simplifying complex ratios and all that good stuff. So just go ahead and be looking at on page 80, numbers 13, 18, 42, 50 through 52, as well as numbers 55 and 56. Now let this be our stopping point. If anybody has questions, I'll stick around. Otherwise, we'll pick up next time on Wednesday. Have a great day.